வச்சுட்டாங்க. அது சீரியல் வச்சுட்டாங்க. அந்த பசங்க நான் தெரியும்.
சார் ஓகே, யூடியூப் இதாகுது. ஆம்ஸ்ட்ராங் சார்.
சொல்லுங்க சார்.
சார் ரிசோர்ஸ் பர்சன் உள்ள வந்துட்டேங்க குரூப்ல.
நேம்
கனகராஜன்.
ஆமாம் ஆமாம். பின் பண்ணிட்டா. சார் ஓகேங்களா?
ஓகே சார்.
ஓகே. இது பண்ணி வச்சா நான் மறப்பேன். இங்கே நாம் பண்ணணும்.
Thank you. Armstrong, sir. Is my voice audible?
Yes, sir. Yes, sir. Yes, sir. Audible.
Okay.
Armstrong, sir. Can you make your phone?
Sir, Sindhu Murugan sir, can I start the session, sir?
Okay, sir.
Okay, sir. Thank you, sir. Good evening, everyone. On behalf of JP College of Engineering, I heartily welcome you all to the third day of our faculty development program. It is our pleasure to have Dr. B. Kanagaraju, Associate Professor, as our esteemed speaker today. He will enlighten us on the topic exploring Bushtown automata, understanding the model of computation for context-free languages. I am confident that the session will provide valuable insights and enhance your understanding of this significant concept. It's my pleasure to invite Mrs. Vinoda Vasagi, Assistant Professor, Department of Computer Science, JP College of Engineering, to introduce our distinguished chief guest, Dr. B. Kanagaraju. Ma'am, please proceed.
Okay, thank you, sir. Good evening to all. This time to introduce our resource person, Mr. Kanagaraju is currently servicing as an associate professor in the Department of Computer Science and Engineering at Sri Shanmugha College of Engineering and Technology, Salem. He brings over 13 years of experience in teaching and research. He completed his ME degree in Computer Science and Engineering from K.S.R. Rangasamy College of Technology, Tiruchankode. He completed his PhD in Information and Communication Engineering from Anna University, Chennai. His expertise spans theoretical modeling of machines, compiler design, Java programming, cloud computing, and artificial intelligence. He is a Wipro certified faculty recognized for training students in Java and J2EE technologies. He has contributed to academia with more than 25 published articles in reputed journals like SCA and Scopus indexed papers, patents, and authorized books. A member of professional societies such as ISTE and ACM. He has been instrumental in curriculum design, accreditation process, and technical training. He is a very wonderful person to deliver the topic of PDA. Now I hand over the session to our resource person, Mr. Kanagaraju. Thank you, sir.
Thank you, ma'am. Thank you for the nice introduction. Whether I'm audible?
Sir.
Sir, audible.
Okay, sir. Okay. Thank you. Sir, whether my screen is visible?
Yes, sir.
Yes, sir, it is.
It is visible, sir.
Okay, sir. Okay. Thank you.
Thank you, sir.
So welcome to the members in the Google Meet as well as organizers. Thank you for opportunity for me to deliver a topic in TOC, Theory of Computation. The topic is going to be Bushtown automata. So we can enter into Bushtown automata. Before going to Bushtown automata, so a little bit about basic introduction. There are different types of grammars are available, which are type 0, type 1, type 2, type 3. So among these type of grammars, so we need machines. So type 3 grammar can be implemented by using finite automata. So with the help of finite automata, we can implement type 3 grammar. So which is the type 3 grammar called as in regular grammar can be implemented by using finite automata. So the next type 2 grammar called as in context-free grammar. So which can be implemented by using a machine called Bushtown automata. So this is the topic we are going to discuss today. I think this is day 3 in day 1 and day 2. So you people may learn a lot related to finite automata. So so today the focus is going to be on Bushtown automata. So then type 1 grammar called as in context sensitive grammar, which can be implemented by using linear bounded automata. So final one is type 0 grammar. This is called as an unrestricted grammar. So this kind of grammar can be implemented by using Turing machine. So little more information about the types of grammar: type 0, type 1, type 2, type 3. So which these things can be implemented by using different machines. Type 3 with finite automata, type 2 with Pushton automata, type 1 with linear bounded automaton, so type 0 with Turing machine. So where these machine required, why we not implement these machine, where these machines can be applied. So if you're taking finite automata, which implemented for pattern matching, lexical analysis, so basic searching, basic search engines. So if you're taking Pushton automata, so which can be used for developing programming languages, arithmetic expressions, XML parsing, etc. I mean, here only, so some of the important things denoted. In many other applications, so these machines can be used. If you're taking LBA, so which is used for syntax checking, compilers, and AI reasoning. Turing machine, which can be used for undesirable problems, especially then AI field NLP, so natural language processing. So these are some of the applications of different types of grammars. Now we may shift our focus to the push-down automata, today's topic. So what's push-down automata? So push-down automaton is a type of automaton that extends finite automata with stack memory. So I think first 2 days you may learn a lot about finite automata, which includes NFA, DFA. So the same, if we're comparing with finite automata with push-down automata, so what we can say, push-down automata which extends finite automata with stack memory. In addition to finite automata, we are going to use stack memory. So this is used, the push-down automata used to recognize context-free languages. So PDA is non-deterministic by nature, but can be designed as deterministic PDA in some cases. Both the things are possible, like NFA, DFA here. So two types of push-down automata possible. One is a deterministic push-down automata, another one is called as a non-deterministic push-down automata. So deterministic push-down automata has a single possible transition for every given input. The same thing, whatever you may heard or learned about. So DFA. So for single possible transaction for any given input. So if you are taking NPDA, so there are multiple possible transitions for a given input. So this is the main difference. So between DPDA and PDA. So this is a small diagrammatic representation. So normally if you are taking finite automata, there is NFA or DFA, just it having only input tape, so finite control machine. So with the help of these two, we may tell whether given input string is accepted or not. So only these two part available in finite automata. If you are coming to the push-down automata, one more thing additionally is that which is called as a stack. We can use stack for implementation of push-down automata. So within stack, some information we can store. So this is a formal definition of PDA. So PDA is formally defined by using 6 tuple, so which includes Q, which denotes finite set of states, sigma denotes a set of input alphabets. The next one is denoting stack alphabets. The next transition, del denote transition function. So Q naught denoting initial state. So F denoting set of accepting or final state. So within among these things, the del, the transition can be defined so as del of Q comma A comma X is equal to P comma Y. Among this, Q denote current state, A denote input symbol which we are reading from the input tape. So then X is denote top of the stack. So this is the current state. So from that, if you are seeing this information, what we are going to do? What's the transition? So equal to P comma Y. So the Q can be the next. So we may be at same state whenever reading an input from a state. Whenever reading an input, either we may stay back at same state, or we may move to the next state. For example, for an input A, from a state Q, we may either go to some other state, or we may be stay back at the same state. So here assume P is going to be the next state. So Y is going to be stack operation. So whenever we are reading an input, so whenever we are reading an input from user, not user, whenever you are reading an input from tape input symbol from a state, so we may move to some other state as well as we can do some operation. Here why denote push, pop, or no change. So we'll discuss in detail. While discussing an example, we will get more idea about this transition. So the next PDA consists of the following things. So finite control, there is a set of states. So input tape, so which contains input symbols. So the next we are having a stack, so provides additional memory to store symbols. You are familiar with, I think most of them familiar with this stack, last in first out order. So the next transition function, which governs state transitions, initial state. So from which state, from which point we are going to start, there is an initial state. So final state, which is going to be accepting state. Here, so acceptance of PDA. There are two possibilities are there. But if you're taking finite automata, so whether a particular input string is accepted by finite automata is decided by only one option, that is called as the final state. After reading set of inputs, if we reach the final state, so then the given string is accepted by the language. So only one option in finite automata. If you're coming to the PDA, there are two options are available to check whether given string is accepted by machine or. So one is PDA with empty stack, acceptance by empty stack. Another one is acceptance by final state. So what is acceptance by empty stack? A PDA accepts a string if the stack is empty at the end of input processing. So from input A, we are reading symbols one by one. We are moving state by state. After reading all the input symbols, if we reached so empty stack, then it is called as an acceptance by empty stack. So another thing is PDA accepts a string if it reaches a designated final state at the end of input processing. After reading all the input symbol from the tape, if we reach final state, then the particular string is accepted. So these are the two ways we can so ensure whether string is accepted by PDA or not. So little bit difference we can discuss between finite automata and full-stone automata. So in the future of memory, no extra memory available within finite automata. So only memory is available to store the inputs. That is called as an only input tape is available. Within that we can store input symbols. If we are taking full-stone automata, in addition to that input tape, we can also use stack to store certain information. Then next, language type. Finite automata only recognizes regular languages. PDA, which recognize context-free languages. So if you're taking finite automata, less powerful, but full-stone automata having more feature that more powerful. So examples. So if we want to find so whether an input string contains even number of ones, simply we can done with finite automata. So the next, so full-stone automata. So whenever so balanced example, balanced parentheses. So to check whether parentheses are balanced, so we can done with the help of this full-stone automata. So hope I am audible. Please, anyone confirm, is there any deviation?
No, sir, you're audible.
Okay, thank you. So now we can move to the problems. So we can take a language, a power n, b power n. So where n greater than or equal to 1. So what we can say within this. So we can't develop finite automata. So for this language. So why? Suppose if you are taking so how many number of C occurs, same number of B should be occurs. So this cannot be implemented by using finite automata, but this can be implemented by using full-stone automata. So how can we implement? So we can see before going to this some information, some theoretical information how to implement. Here a string belongs to the language if it consists of A repeated n times followed by B repeated m times. So where n greater than or equal to 1. So number of A's and number of B's should be same. So then only this language will accept. Suppose an input string is given, we need to check whether that input string is accepted by this PDA or not. For example, AAA followed by triple B. So this is then accepted by this one. If you're taking some other so AA, BB, triple B. So this is the input string is not accepted by this language L. So how do you check whether input string is given, whether the input string is accepted by this language or not? How can you identify, how can you find? For this we are going to design PDA with the help of this machine PDA. So PDA machine we can identify whether we are going to design a PDA for this language. This context-free language are going to design a PDA. So whether this PDA is going to be accepting the string or not. So this can be verified by using this machine. So how can you do it? So we can directly move to the so implementation. So we can start. We can assume. So for each and every A, we are going to store a value in stack that is called as in capital A. For each input symbol A, for example, input single input is going to be AA, BB. Assume simple example, we can take it AA, BB. So for each A, so this is available in the tape. The input is going to be stored within input tape. Which is stored in input tape. For each symbol, so for each input symbol, so we are going to take a tape symbol. For example, for A, we are going to take an input symbol, tape symbol capital A. So assume we are starting at some state that is called as in Q naught. Assume we are start state is Q naught. So from this, if you are reading input symbol A, what operation you are going to do? So initially assume the stack contains, assume this is stack. So stack contains initially jet naught. Assume stack contains a symbol which is called as in jet naught. So by default we are having this jet naught. So now if you are reading an input A, what we are going to do, what transition we are going to do. So if you are reading A is an input symbol, the next top of a stack is going to be jet naught. So what we are going to do for this A, we are going to push capital A. So any symbol we can push it. For example, I am pushing A. So there is A occurring in the input symbol. Top of the stack is jet naught. We are going to push A into the stack. So now what about the stack? A is jet naught. A is jet naught. So we are reading A. During that time, we also check stack. We are also check stack. If stack also contains jet naught, input symbol is A. What we are going to do? We are going to push capital A. We are going to push capital A. Here, capital A is a stack alphabet or stack symbol. So what about stack now? So A jet naught, top of the stack A. So previous top of the stack is jet naught. So this is one operation we are going to do. After completing this operation, I am stay back at the same state. So one more thing. If I am reading one more symbol, second I am reading A. Top of the stack is capital A. What I am going to do? So I am going to push A. I am going to push A for this A. So now top of the stack is going to be A. So the next. So how many? So whatever A is available in the input string, so which is accepted, and we are stay back at the same state. The next, suppose we are reading input symbol B. We are reading input symbol B from the tape. Then next, top of the stack is A. What we are going to do now? So we are going to pop. Now we are going to pop. First, what we are going to do? We are pushing all the A's. Whatever A is available, we are going to push it into the stack. For example, so this example, there are two A's are there. Initially, tape contains Z0. So there are two A's. We are pushing all the two A's. So once, if you are seeing B, we are going to pop. We are going to pop. For each B, there is a is going to be popped. So for each A, we are going to push capital A. For each A, we are going to push capital A. Once if you start seeing small b, we are going to pop an A from the stack. For example, first B, we are going to pop this one. For second B, we are going to pop this one. So the input symbol is over. After reading all the input symbol, we are checking stack. If it contains Z0, so the given string is accepted. So the concept is accepted by final state. Here accepted by final state. Suppose if you are whenever you are saying B, so we are going to also check whether top of the stack is A. So if the top of the stack is A, we are so popping that one. That is denoted by epsilon. Epsilon here denotes popping this top of the symbol. So once when we are seeing B first, we are switching state from Q0 to some other state Q1. So after this, whatever symbol is there, so whatever inputs we are reading for B, if it is top of the stack A, we are removing this. We are popping that symbol. We are popping the A. Whenever we are seeing B, if it is top of the stack A, we are popping it. This operation is going to happen repeatedly. So finally, suppose there is no input symbol. All the input symbols are red. So if the top of the stack contains Z0, what it means? Number of A's, number of B's are equal. So we can assume. So we are not going to change anything. We are keep Z0 as it is. We are moving to the final state. For example, QF. Something called QF. So this is start state. This is an PDA for the language. Else equal to A power n, P power n. So now we can check with this example. One more small example we can take. Assume the input is going to be so AA. So triple A, triple B. Assume we are taking another input triple A, triple B. So that's all about the tape. This is an input tape. So we can check whether this string is accepted by this language or not. Whether this is accepted by this language or not, we are going to check by using with the help of this PDA. This PDA. So we are taking A. We are starting A. We are at Q0. We are reading A. So what is the initially? What is the top of the stack? So we are don't consider these things. Now we are dealing with this one. Assume what is the top of the stack now? Initially the stack contains Z0. Initially the stack contains Z0. So what is the input symbol? A. What is the top of the stack? Z0. Which transition is matching? A is Z0. Input A, top of the stack is Z0. What we are going to do? We are going to push A into the stack. We are pushing it. First input symbol is so we read first input symbol. Then next we are going to read second input is A. So we are reading A. What is the top of the stack? Capital A. So which one? Not this one. This one now. A. Top of the stack is A. Input symbol is top of the stack A. What we are going to do? We are pushing A into the tape. Not tape, stack. We are pushing A into the stack. So now this is for second is over. We are say back at the state Q0. Then next we are reading another input symbol A. Next input symbol is A. So what is top of the stack? Capital A. A. So what it is going to be now? We are going to again push A into the stack. So generally, if you are reading A from the input symbol, we are going to push a stack symbol A into the stack. So that's it. Once if you are saying B, we are going to pop in tape symbol from the, we are going to pop a stack symbol. So from the stack. So we are seeing B, what are we going to do? B, top of the stack A. We are in Q not state. Input symbol is B, top of the stack is going to be A. So what are we going to do? We are going to popping this symbol, that is stack symbol A, we are going to pop now. So this is popped. So at the same time, we have reached to the Q1. Now we are state at Q1. So what is the next input symbol? B. Now currently we are in state Q1. Input symbol is B. What is the top of the stack? A. So B, A. There are two transitions available for this particular state. This one, this one. So as per the input B, what is the top of the stack? A. This is matching, not this one. This is matching. B, top of the stack A. We are going to pop that top of the stack. This A is popped for this input B. Next input B. What is the top of the stack? Still A. The same this transition once again going to be executed. B, top of the stack is going to be A. So we are going to pop this top of the stack A. We have popped this one. So all the input symbols are red. What will be there in the tape? Nothing. There is an epsilon. So remaining things are generally are called as an epsilon in the tape. So what is the next input symbol in the tape? Epsilon. What is the top of the stack? Z0. This is not matching. This transition is matching. Input is epsilon, top of the stack is Z0. We are keeping Z0 as it is. Then we are switch over to the another state called QF. So QF is the final state. So after reading all this input symbol, we have reached to the final state. So then we can say the string AAA BB is accepted by, so this pushed on automata as well as which is denoted by this language. So I'm more AA or AAA, or we can take AAA BB. So whether this input is accepted by this language or not, we are checking by using this PDA. So initially assume initially stack contains Z0. Assume initially stack contains Z0 by default. So now we are initial state is Q0. We are at Q0. So Q0. So we are first input symbol is A. So input is A. What is the top of the stack? It's Z0. We are at Q0. There are three transitions of that. This is one transition. This is second one. This is third one. So among these three transitions, which one is matching? Input symbol is A. Top of the stack is Z0. So this one is matching. These two are not matching. This one is matching. This one is going to be executed. What is the operation? Input symbol A. Top of the stack is Z0. What we are going to do? For this input symbol A, we are going to push capital A in the stack. After that, we are at same state. We are at same state Q0 itself. We are reading next input symbol A. Top of the stack is capital A. Which one is matching? A, capital A. This is not. This is matching. So what we are going to do? We are going to push A for this A. So one more A we are going to push while reading the second A. Next we are going to read next A. So we are staying back at Q0 itself. A. What is the top of the stack? A. So this transition is going to match. This transition is matching, which is going to execute A, comma A. So we are going to push A in the top of the stack. This is previous top of the stack. This is current top of the stack. Generally, we are denoting two things. So this is actual top of the stack. Second one is previous top of the stack. We are going to push A for this A. The next input symbol is B. What is top of the stack? Capital A. This is not matching. This is not matching. This transition is matching. So B, input symbol, top of the stack is A. So what we are going to do? We are popping that one. We are popping this A. We are popping this A, as well as at the same time we are switching from Q0 to Q1. The next, now currently we are in Q1. The next input symbol is B. We are reading. So input is B. Top of the stack is A. So what we are going to do? So top of the stack is A. So input B, top of the stack is A. We are going to pop. We are going to pop. So the second A is going to be popped. After this, epsilon, no input, that is epsilon. Next is epsilon. What is the top of the stack? A. Is there any transition? For epsilon A, only BA is available. Epsilon Z0 is available. There is no transition created in the PDA. No transition in the PDA for input epsilon top of the stack A. So what will happen? We can't move to any state. We are at the same state Q1. As well as we have reached end of the input. After reaching end of the input string, we are checking we are currently at which state. We are at state Q1, which is not final state. So the given string is not accepted. So if we have reached QF, then only we can say the given input string is accepted by this PDA. So this is not accepted. So this is a language. So for this language we have implemented a push-down automata. So they have states are Q0, Q1, QF. These are transition. For these two transitions, we are stay back at the same state. For this transition, we are moving from Q0 to Q1. So for this transition, so after completing this transition, we are stay back at Q1 itself. For this transition, we are moving from Q1 to QF. So this is called as an so for a same input symbol. So AA, but top of the stack is different. These two are not same. So input symbol is A, but top of the stack is going to be different. So if you have any doubt on this example, you may ask, I will clarify. If anybody having any doubt, you may please ask.
Sir, we cleared.
Okay.
Proceed
okay.
the next problem.
Okay. Thank you. So we can move to the next problem. So it's a palindrome. There is a language, consider language else equal to W. W is a palindrome. So how to check so whether given string is in this language or not. So the language is denoting a palindrome. If we are giving an input string, so whether that input string is present within this language or not. To check, we can develop a PDA. So now we are going to discuss this one. We are going to develop a PDA for palindrome. So first we can design a PDA, then we can go with example. Assume we are start with Q0. So starting state. So actually palindrome, some example string already we have here. Radar, simple example. String we can take radar. So this is an palindrome string. Like that, there are many palindrome strings are available. So L is a language which contains many strings. All the strings are palindrome. So I am writing some string. Whether this string is available within this language or not, how do we check? With help of PDA, we are going to check. For this, we are going to design a PDA Q0. So assume initially top of the stack is going to be Z0. During that time, so I am reading a input here. I am reading an input. For simplification, I am going to use some simple example. For example, A. So B. A. So I am taking this example. So instead of this one, so A, B, A. So this is called it as an input string. So Z0. So input symbol is A. So what we are going to do? So top of the stack is Z0. We are going to push A into the stack. So input symbol is A. Top of the stack is Z0 means we are going to push a type symbol, push the stack symbol, not type symbol, push the stack symbol A into the stack. So the next, suppose input is A, top of the stack is A. What we are going to do? We are going to push A. So A is we are pushing for this new input symbol A. So this A, we are denoting secondly. This is previous top of the stack. This is current top of the stack. It's the same thing. Z0 is the previous top of the stack. So current top of the stack is, we are going to push A for this A. For this A, we are going to push A. Suppose if you are seeing something, so assume which the palindrome string contains only two input symbols A and B. A and B. Only two input symbol A and B. So now if you are seeing B, what we are going to do? So if you are seeing B, top of the stack is going to be capital A. We are keeping A itself. We are not pushing, we are not copying anything. It is not necessary to push or it not necessary to pop. So if we not record, we don't need to push, we don't need to pop. Simply, so we don't need to do any operation, push or pop. Simply, we are keep the same thing. So input is B, I'm in Q0. If the input is B, the top of the stack is A. So we are keep A itself, we are moving to the new state, which is called as in Q1. After reaching Q1, so what I'm going to do, I am going to do pop operation. So for the input is A, if top of the stack is A, I'm going to pop this A. For all the input A, we are going to pop capital A. So now at the end, so no input, all the inputs are so having a transition. Then finally there is no input. Epsilon, top of the stack is Z0. What we can say, simply we can say, we can move to the final state. So that we are keeping Z0 as it is. So this is an PDA for accepting the string. So string contains only two letters A, B. String contains only, so input symbols only, these are the two input symbols, sigma, A, comma, B. So we can take this input AA, BAA. So we can check whether this PDA, this is actually this is a palindrome string. So we can check so whether this is accepted by this PDA. So then only we can tell that string is present within this language. So assume initially Z0 is there. First we are taking the first input. So assume we are put it in a tape. The input symbol are put it in a tape for clear visibility. AA, BAA. So after that, the tape symbol contains epsilon. So it's an infinite input tape. Contains input symbol. This is an infinite stack. So now first, what is the first input symbol? We are initially always we are at start state, which is Q0. We are in Q0. We are reading input symbol A. So we are reading input symbol A. So what we are going to do? So input symbol is A. We are, what is the top of the stack? Z0. A Z0. What operation we are going to do? We are pushing capital A into the stack. We are pushing capital A into the stack. So the next. After that, we are stay back at Q0 itself. Then we are reading next input symbol A. So what is the top of the stack? Capital A. Which transition is matching? The second one is matching AA. Input symbol A, top of the stack is A. So AA, this one is matching. What are we going to do? We are pushing one more A into the top of the stack. The next, stay back at the same state Q0. We are reading next input symbol B. What is the top of the stack? A. Which transition is matching? BA. So input is B, top of the stack is A. BA not matching, BA not matching. This one is matching. So what we are doing now? So we are not push or pop anything. Just simply we are switching from Q0 to Q1. After reading B, simply we are moving from Q0 to Q1. Currently we are at Q0 state. Currently we are at Q1 state. We are reading next input symbol A. Currently we are in Q1. Input A, top of the stack is A. So what are we going to do? AA. We are going to pop A from the stack. This is popped. Now top of the stack is this A. This is now top of the stack. So what is the next input symbol? A. Top of the stack is A. From Q1, input symbol A, top of the stack is A. So what we are going to do? We are going to pop A from the stack. We are popping this. This is also over. So all the input symbols are red. What is the next input symbol? Epsilon. What is the top of the stack? Z0. Epsilon Z0. We are keeping Z0 as it is. Then we are moving to the next state, QF. All the input symbols are red. So we also check what stack contains Z0. So we can say, so this input string is accepted by this finite automata. So this input string is palindrome because this is present within this language. So it is difficult to check manually. So language with palindrome with two input string AB, there are many things are there. So AA, this is also palindrome. Next ABA, next AA, B, AA. So like that, there are many infinite strings we can create. So double is a palindrome with two input symbols A comma B. There are many possible strings are available. So if you want to check manually, it is difficult. There is a string is given. How do you compare? So there are lakhs of more than lakhs of the strings available within this language. It is checking manually. It is checking is too difficult. That's why we are trying to create a machine. With the help of this machine, simply we can check. So we can't compare first string with first string, second with this one, third one with one. How do we check? Which contains many strings, we can't check manually. If you have developed a PDA, simply we can use it, check whether a string is accepted or not. This is a PDA for this language. So if you are checking this, whether string is accepted by this PDA or not. If it is accepted, this is definitely this is present in this language. Otherwise, we can say this is not available in this language. So one more example we can see. For example, AB. So we can check it. After that, epsilon is there. So we are stored initially stack contains Q0. Input symbol is A. Top of the stack is Z0. We are insulator Q0. A Z0. We are pushing A into the top of the stack. Next input symbol B. What are we going to do? This is not matching. This is not matching. B, top of the stack is A. Input symbol A. Input symbol B. Top of the stack is A. B comma A. So this transition. No change in the stack. Just we are switching from Q1. Now we reach to Q1. What is the next input symbol? A. What is the next input symbol? A. So what is the top of the stack? Capital A. This is matching A. So what are we going to do? We are going to pop this one. We are going to pop this one. The next input is B. We are in Q1. Input is B. Top of the stack is Z0. B Z0. There is no transition. Only two transition we have created. A epsilon Z0. B Z0. There is no transition. We are stay back at the same line. We are stay back at the same state. We are not moving any state. What is the next input symbol? Epsilon. So we reached end of the string. We are checking. We checking whether we are reached final state or not. No, we are not reached final state. We are not reached final state. We are at Q1 itself. So we can say the string is not accepted by this PDA. So this is not accepted by this language because this is not a palindrome string. So this diagram is denoting for PDA accepting final state. So for this, how do you create PDA accepting by empty stack? PDA accepting by empty stack. So what we can do, small change. So what we are going to do? So instead of this one, so we are reached to some other state Q2. Suppose if we are reading epsilon Z0, we are keeping Z0. Just we are switch over to the new state Q2. Or so I'm deleting and once again writing for. So this is the language. Initially we are at Q0. So there is two inputs for an input symbol A. Top of the stack is Z0. We are pushing A Z0. Then next A. Top of the stack is going to be A. We are going to push A. What are getting A. So if you are seeing B, top of the stack is going to be top of the stack A. So we are keeping A itself and we are moving to a new state. This is Q1. So then next, so this is once again we are reading B. If the top of the stack is A, we are going to pop. So the next, if you are seeing input is epsilon, if the top of the stack is Z0, we are popping this Z0 also. We are popping this Z0 also. We are moving to some other state Q2. Some other state Q2. So I have missed a few more transitions. Suppose input may be like this. For this input, not only like this AA, B, AA. So input may also BB, A, BB. So like this, or B, AB. This it may be like this. So for this, these kind of things. So start with A only I have written here. Start with B also we need to write. So suppose input is B. So top of the stack is Z0. We are going to push B. Suppose input is B, top of the stack is B. We are going to push PB. This also need to come. These kind of inputs. So the previously which we discussed for palindrome. So only the part we had the discussion. Only this kind of string start with A only accepting. Suppose start with B. We are not added transition. Now I'm writing this one. So once if you are seeing A, top of the stack is B. So we need to A. So this top of the stack is so not input A. Sorry, input A. Top of the stack is B. We'll keep B itself. We are moving to this new state. Then input so for the input. So sorry, this one is A. For this one is A. So for this one is B. Top of the stack is going to be B, where epsilon it. Actually, so exactly we can't say the palindrome. So PDA. Sometimes some inputs. So we can't check exactly. We can't implement. So fully with PDA for this palindrome problem. So we need to go with Turing machine. So Turing machine, we have to use it. Turing machine to implement complete case of palindrome. For some of the palindrome cases, only this PDA is possible. All the palindrome strings, all the palindrome strings with language, we can't use this PDA. So only with restriction only we can use it. If you want to need complete implementation, so we should go with a Turing machine. So like this another problem. So this is balance parenthesis. To check balance parenthesis, we can also use push-down automata. But so multiple symbols, it is difficult. There is only one symbol. Simply we can implement. So what are the applications of PDA? So the PDA can be used in different applications. So one is syntax analysis in compilers, parsing in natural language processing, we can use NLP. The next, implementing recursive function call in programming. So we can use this PDA. Evaluating arithmetic expressions, we can also use PDA. These are some of the applications of PDA. So the next, this based on this one, there are two theorems of that. So one is PDA with final state. From PDA with final state, we can convert it into PDA with empty stack. So another one is reverse. So PDA with empty, from PDA with empty, convert it into PDA with final state. So the first one is PDA with final state to PDA with empty stack. So how can you do it? So ensure that whenever a final state is reached, the stack is empty. In this case, so whenever a final state is reached, the stack is empty. Steps for this conversion. So introduce a new start state q new. So we are going to introduce here. So normal this is PDA with final state. Assume there is a sum state. Finally, there is a final state. This is that. So in the PDA with final state. So while we are trying to convert with to the empty stack, we are going to add a new state that is called as in q new. So this is going to be start state. So the next, so push the special symbol z naught. We are going to push the special symbol z naught into the stack. So there is a second operation. We are going to push z naught into the stack. So the next, so whatever transitions are happen here, so we have to write. Then finally, so when the original PDA reaches the final state, ensure that stacks become empty. So add an epsilon transition. So from the final state to new state QF. So while moving this state to this state, we are going to remove epsilon, remove z naught, and so remove z naught. So input is epsilon, we are going to remove z naught. Top of the stack is z naught, that is going to be popped. Actually, input is epsilon. From the final state, input is epsilon. If top of the stack is z naught, we are going to pop it. We are reaching to the final state. No, we are reaching state to some state called QF. Actually, this is the final state. So this is some other state. So now stack is going to be empty. Now stack is going to be empty. So this is the way the conversion from PDA with final state to PDA with empty stack. So the next one is PDA with empty stack to PDA with final state. So for this, so there is a start state, then number of transitions. So there is a last state. So this is something called the Qn. This is Q0. Starting with Q0, finally are reaching to Qn. After reaching Q1, so we are checking, after reaching Qn, we are checking, after reading all the input symbols, so we are checking whether stack is empty or not. If the stack is empty, this is PDA acceptance by empty stack. This is the input, PDA acceptance by empty stack. How do we convert this into PDA acceptance by final state? So introduce a new final state QF. So whenever the stack becomes empty, transition to QF using an epsilon move. So top of the input is epsilon, top of the stack is nothing. So we are not pushed for pop anything, just we are reaching to the final state. So this is converting from PDA with empty stack to PDA with final state. So there is no final state here. We are adding a transition towards end to reach the final state. During that time, the stack is empty. So input is epsilon. We are not reading anything. So just we are moving to the final state. So this is so formal definition. This is general things. Just we are introducing a new state in the empty stack concept. We are introducing a new state. So, but how do you define formally? How do you define formally? So, let PDA M is equal to Q sigma. So, tape symbol, the not stack symbol, del transition Q naught, Z naught. So, pi, the next, we have PDA accepting by empty stack. Assume there's a PDA M. We are going to construct a PDA M dash. So, what we are going to do? We are going to, here in this case, why pi is given, no final state. PDA with empty stack, we are not checking final state reached or not. We are checking whether stack is empty or not. So that's why here it is. So final state, here it is null. Why they are giving pi null? So because BD accepting the empty state, we are check whether stack is empty or not. Whether stack is empty or not. So now we are converting. So this PDA with empty stack to PDA with final state. This is an M dash. So for this we are adding. So towards then we are adding a final state. We are adding a final state. So after reading all the input symbol, so if the stack is empty, we are reaching to the new state. We are introducing a new state that is called as in QF. That is a final state. So for final things, what are going to add a transition? So we are in a state, there is no input symbol, Z naught equal to QF Z naught whenever M reaches an empty stack. The same way, formal definition for PDA with final state to PDA with empty stack. So this is a PDA with final state. You can see. So a number, set up state, set up input symbols, set up stack symbols, transition, Q naught start state, Z naught initial stack symbol. We have denote set of final states. So this is PDA accepted by final state. So the next, if we are trying to convert this into another PDA M dash with empty stack. So set of states, the next input symbol, tape symbol. Additionally, we are having Z naught. Additionally, we are having Z naught. We are adding it because we are emptying stack. That's why we are adding one more Z naught. The next, this is a transition. This is we are adding a new state. Initially, we are adding a new state that is coming. So the next Z naught. It's the top of the stack. There is a initial stack symbol to no final state. So PDA with final state, as the final state is available. PDA with empty stack, no final state. We are identifying the accepting inputs by using whether stack is empty or not. In this case, we are checking whether stack is empty or not. No symbol in the stack, string is accepted. In this case, we need to reach the, so we have to check finally whether we have reached stack with only Z naught, as well as we are checking stack with Z naught whether we have reached final state. Actually, whether we have reached final state. So if you reach final state, the string is accepted in this case. In this case, the stack should be empty. So these are the two things, two theorems, or there PDA with final state to empty stack, PDA with empty stack to final state. So that's all about so my presentation regarding PDA. So if there is any queries, so welcome.
Participants can raise your questions to the chief guest for clarify your doubts.
No, sir, it was clear.
Thank you very much, sir, for your wonderful presentation on today's topic, sir.
Yeah. Thanks. So thank you, sir. Thank you for the opportunity for me to take PDA. So in this application in FDP.
Thank you, sir. We hope that today's enlightening session led by Dr. Kanagaraju has enriched your knowledge and provided valuable insights into exploring boost down automata, understanding the model of computation for context-free languages. We kindly request that you take a moment to complete the feedback form, which can be found in the chat box. Your response will serve as a confirmation of your today attendance for today's session. Thank you for your cooperation. We eagerly await your return at tomorrow's session. To maximize the experience, kindly arrive on time. Once again, we heartily thank to Dr. Kanagaraju for spending your valuable time with us today. Thank you, sir.
Yeah. So once again, I thank the management, the coordinators, and the people those are attended today. So thank you for everyone. Thank you for the opportunity.
Thank you, sir. We extend our thanks to all the participants for your active participation and engagement today. Thank you, all the participants. Thank you all.
Thank you so much, sir.
Thank you, sir.